This problem is a little bit tricky, mostly because of this spring component. So let's start by just reading the question. Shower curtain rod consists of two telescoping cylinders connected by an internal spring with K equals 750 newtons per meter. All right, let's write that down. And a relaxed length of L naught equals 2.6 meters. And here's our picture. The rod is placed between two walls a distance L equals 2.5 meters apart. All right. So that must mean that the spring has to be squished a little bit from its equilibrium length. And it's going to be squished a little bit by some delta L that's equal to L naught minus L, which is 0.1 meters. Okay, so a wet towel is hung from the rod on a coat hanger, a distance D equals 0.5 meters from one wall. So that's over here. If the rod has a mass of 2 kilograms and the towel and hanger have a combined mass of 4 kilograms, what must be the minimum coefficient of static friction between the ends of the rod and the walls so that the rod does not move? So it does not move. We can assume the center of mass is in the middle. All right, so let's just start with a free body diagram. So here's the rod. So what forces do we have? Well, we have the weight of the rod. The rod is touching the walls. There's going to be a normal force acting on each end. So this is F normal 1, and this is going to be F normal 2. And they both point in because they have to be perpendicular to the surface, and they're acting on the rod, not the wall. Okay, and then the rod isn't sliding down the wall, so there must be some friction forces. So we have one that goes up like that, so this is the force of friction 1, and over here we have force of friction 2. And then last force we have is the force from the hanger. So that's the force from the hanger, and that's a distance. This distance here, let me get one more color. This distance is D, and the total distance is L. Okay, so this problem is mostly tricky because you have to figure out what the normal force is. Now, we know that the normal force that the wall is exerting on the rod, so that's this one, has to be equal and opposite to the force that the rod exerts on the wall. And the rod is really just a spring. So this normal force is a spring force. And the spring force, the magnitude of the spring force, is going to be equal to the spring constant of the spring times how much the distance it's compressed from its equilibrium length. So that means that Fn2 and Fn1 are both going to be equal to K times this delta L. Oops. Okay, so this problem is a statics problem because we're looking for the coefficient of static friction so that the rod does not move. And in particular, we're looking for the minimum coefficient of static friction. So let's start by doing the torque equation. So if we sum the torque, we need to choose a pivot. So we want to choose a pivot that eliminates some forces we don't know. So I'm going to choose this as my pivot. So the sum of the torques is going to be, so we're going to need to include the gravitational force. So that's at a distance of L/2. And then we're going to include, and that's got to be negative because it's going to rotate it counterclockwise. And then FH is also going to rotate counterclockwise, and that's at a distance L minus D. So that's this distance right here. L minus D times FH. And then what about the normal force? So Fn2 has no component that's perpendicular to the lever arm, so that does not exert a torque. But the force of friction does, and it exerts a counterclockwise torque, so it's going to be positive, and it's at a distance L from the pivot, and we multiply by F mu2. And that has to sum to 0. Okay, so now what are we looking for? We're looking for the coefficient of static friction. So we have to substitute some of these forces. So let's do that. So we have minus L/2. Fg is the mass of the rod times g. And we subtract that. Fh is the gravitational force due to the towel. So that's going to be the mass of the hanger and the towel. Just lump them together, times g, and then we have to add L times the friction force. The friction force, we know that the force of friction is mu times the normal force. So we multiply by mu Fn. That has to be equal to 0. And then we said, well, the normal force is K delta L. Okay, so let's rewrite this a little bit. So let's take this term and substitute in Fn, which is K delta L. And then let's move all of these terms to the other side. That's going to be equal to L/2 m rod g plus L minus D m towel g. And then we want to solve for mu. So let's do a little bit of rearranging. So we can pull out a g and multiply that by L/2 m rod plus L minus D m towel. And then we got to divide that by K L delta L.